Yes. Okay, we can start with Reinhard Genzel, a 40-year journey. Please, Reinhard, proceed.
Thank you, Raymond. Let's see, the last time I guess I talked at one of your conferences must have been about 9 years ago. And I'll hope I can show you that lots has happened in this field and some amazing scientific progress as well as technical progress. And so I want to do this by describing this in a more global way. That's why I call it the 40-year journey. I could have called it the 100-year journey, as you will see in a second, because of course, this is all part of a bigger story. Our story, my story, started about 40 years ago when I joined Charlie Towns's group in Berkeley. And as you will see from my talk, that's when when I got involved in this project to test the massive black hole paradigm. And with it, general relativity in the regime where it has not been tested yet, by using the center of our Milky Way. Now, of course, as you might imagine, this has been a true journey in the sense of many people working on this over time. As you will see, technology and innovation in technology plays an enormous role in this, as it does in other fields, of course. And so I'm very grateful to the many young people and not so young people who've been working with me lately using interferometry as a new tool in the infrared to achieve micro-arc-second astrometry, which is really a new game in astronomy, as you will see. Now, of course, we are really celebrating also more than 100 years of general relativity, and I don't think I need to go in any detail here to explain that, of course, the theoretical work, which started with the famous talk of 1915 in Berlin, and then Schwarzschild's solution 1 year later, Kerr's solution in 1963, Roger Penrose's more general discussion of the singularity and the possibility in nature to actually realize black holes. And then the first attempts by Hawking and others to understand the still not understood tricky aspects of the quantum nature of such a black hole. Okay, so all of this, of course, by itself took 50 years to mature and is still not finished. And as you well know, it took about the same time until the first observational evidence became available that such objects called black holes nowadays might actually be realized. One of them was the discovery of X-ray binaries by Riccardo Giacconi and others, and objects which we now believe are stellar black holes or stellar black holes and neutron stars in spiraling. And of course, as you will see in a second, we have absolutely wonderful, convincing evidence for this now through the gravitational waves. The other one was a discovery of the quasars through the radio astronomy community, showing that there are objects at great distances. We now know quasars to, basically about 800 million years after the Big Bang, very luminous objects between about 1,000 to 100,000 times the emission, the luminosity of the sun, of the Milky Way, all combined within a few light years of a central point. So that, of course, led to an intense discussion, as most of you know, how one can possibly test that these objects really, these quasars really are accreting black holes, which had been the outcome of sort of the majority of the theoretical work in the 1960s. And it took a long time, really. By the 1970s, as you will see, the first serious experiment started on using nearby galaxies in the galactic center to get at this problem with gas motions and Doppler motions. And then over time, two groups, one here in Munich with outliers in France, in Cologne, in Heidelberg, Portugal, and so forth, and one in UCLA, led by Andrea Guess, Mark Morris, Eric Beckman, using the Mauna Kea Keck telescopes, basically set out to use stars as the best way of testing the gravitational potential and see whether there might be a compact object. And that's the story, of course, which I will tell you about. Pretty much at the same time, and still more difficult in technology, was the discovery of the gravitational waves. What a moment that was in 4 or 5 years ago when the first inspiral was detected. And then finally, the radio astronomy community using at short millimeter wavelength telescopes across the Earth in intercontinental interferometry to actually see the accretion zone and resolve it spatially. Now, there's a lot of contact between the work I will discuss from our side and that of the radio astronomers, and we very much would like to see an image of the galactic center, just like what you see here from M87, which was published in 2019. I'll come back to this. So the progress has been very fast in the last few years, and we've made enormous progress in actually verifying the black hole paradigm. As I said, the story in the galactic center started in the 1970s. This was following a paper by Lindenbell and Rees, who basically, of course, analyzed the quasar situation, knowing full well that the resolution and sensitivity of the equipment was not good enough to see any effect of the gravitation of the central black hole, if there's one, onto the environment, like on the stars and the gas in quasars, because of the large distances. So Lindenbell and Rees argued, well, perhaps quasars were just sort of the active part of the massive black hole population in the universe, others not fed at such high rates, but present perhaps in many and perhaps even all more massive galaxies. That hypothesis, of course, has turned out to be correct, and we are following the cosmic evolution of, or co-evolution of galaxies and black holes in great detail nowadays. But at the time, that was sort of a leap of faith, but immediately, of course, pointing the spotlight on the nearest galaxy, namely our own. The only disadvantage being that you cannot observe the galactic center in optical light. Too much dust in between us and the center of the Milky Way, so you have to go to longer wavelengths, the infrared, and you see a modern multi-color infrared image in front of you of the central few light years in the galactic center, using 8-meter telescopes, using adaptive optics and everything else we now have available to us to really look into the central region in some absolutely fantastic detail. So having this kind of opportunity to look at the stars, then the next question is, how might you see that there is a central object in here? Well, the first one, of course, is you might look for a compact radio sources, very much like in also quasars. And indeed, the radio astronomy community discovered one, SgrA star, at the center of this very dense star cluster, which is more than 1 million times denser than the solar neighborhood. And we now know from such observations that this object is indeed very, very compact. We don't have an image quite yet, but the size measurements show it to be less than 40 microarc seconds in radius, I should say. And so this is a very, very compact source, consistent with potentially the accretion zone around a massive black hole. Now in Berkeley, Charlie Towns, having turned astronomer from his earlier work on masers and lasers, started to build equipment, spectroscopy equipment in the few micron to 10 micron region. And he and his group, and I joined this group then as a postdoc, were looking at the gas in this very central region. Again, you see SgrA star, but in addition, the pink clouds, there is ionized gas, streamers of ionized gas, obviously orbiting in some fashion around the radio source. Likewise, the green is neutral gas, which is also moving. So we, at that time, were able to build equipment to see the Doppler motions of these gas clouds, and they were large, much larger than you would have expected from the sum of all the stars, which you see here in blue. So by the mid-80s, the Towns group wrote a Nature paper where we told everyone that there was a few million solar masses in the central few light years, and it was unlikely to be the star cluster. Basically, the evidence goes from mapping out the mass enclosed within radius as you go away from SgrA star, and then you see at large distances that, of course, the mass increases, which is because there's an extended mass due to the stars, but within about 1 parsec or so, and inside of that, these innermost gas clouds showed a more or less constant mass distribution. So that would be the evidence for a compact mass, and that was a few million, 2 to 4 million solar masses. Now, is that a black hole? Well, it could be one, but obviously you are working here at about 10 to the 6 times the event horizon size. So there are many other possibilities. There could be dense clusters of neutron stars, other clusters of very faint stars, et cetera, et cetera. So that is certainly not good enough to be a very convincing piece of evidence as seen from nowadays. Also, many people felt that gas motions might not be reliable traces of gravity because magnetic fields, of course, are likely to be strong in this region and would change the motions of the gases, especially the ionized gas. And there could be stellar winds and other things which would push the gas around. So many people in the field felt, no, this is not yet good enough. You have to go closer, and you have to have a tracer which is a more likely, more believable tracer of the mass distribution. But that required technology. We didn't at that time actually have good enough imaging detectors in the infrared the American military had, but only over the next 5 or 6 years was it possible to transfer that technology over to the astronomy community in the US and then here in Europe. So when I started in Munich as a new director, we made that one of our new aims to build basically cameras and then also imaging spectroscopy apparatus to look into the galactic center. Another problem, of course, is when you take a big telescope in order to have good resolution and look at a star, well, then the waves coming from that star are distorted by the turbulent atmosphere. That is a big effect in the optical, such that if you integrate without doing anything, the sharpness of the image is about 1/10 of that which you might get through diffraction. And as you well know, the solution nowadays is adaptive optics. you basically sense the distortions of the atmosphere. Then you have a deformable mirror in the path, and then you can take that initial distorted image, which you see on the right, and make it sharp at the diffraction of the telescope. You see the first area ring. So that technology became possible and then routine in the 90s and early 2000s, such that 8-meter telescopes nowadays, of course, work at high resolution, 50 milliarcsecond resolution. Now, not always do you have a star near the object. And so another technology which we had to develop was to basically create your own star near where you want to observe by shooting up lasers in the upper atmosphere, focus it there, and use resonant backscattering by sodium atoms to basically sense the distortions of the atmosphere with your own artificial star. So all of these technologies had to be introduced over the next years, and I'll come to another one next, and have improved the sensitivity and angular resolution by factors between 10 and 1,000 over these years. So the two groups working in the 1990s, we from the telescopes of the European Southern Observatory, initially a 3.5-meter telescope, and then the VLT 8-meter telescopes, and then a little later, Andreas' group using the Keck telescopes basically started making images, astrometric images, with this equipment of stars near SgrA stars. So this image here, in fact, is a superposition of images from 3 different years in red and green and blue, and SgrA star is that yellow-green cross, and the light month on this scale is this circle. So you see, obviously, from superposing these images that close to SgrA star, there are some objects, some stars, which move so fast that the images are easily separable from year to year to year. And if you look at the upper right, then you see how much that would be in terms of a true velocity, and it comes out to be several thousand kilometers per second. That's something which we published in 96 and 97, and a year later also the Keck group came out with the same result. And when you look at the motions here, you immediately see that the Kepler's laws work quite well for you, in the sense that the motions inside near SgrA star are obviously much greater than the outer ones, which look like white stars. And that's basically 1/² which works for you. So if you then interpret these average motions in terms of a mass distribution, what you find is that there is, about 2 to 4 million solar masses within about a light month. So that's the same result as we had a decade earlier with the gas, but now with a reliable tracer and a little further in by some factor of 3. So the question again comes, is this a black hole? And the answer is, it could be, but of course, while we've moved inwards, we're still several 100,000 away from, in terms of event horizon radii, and so other things could perhaps fit in there. Plus, the other thing is, this is a statistical measurement. You can measure the motions on the sky, Vx and Vy. You can also measure through spectroscopy the stellar velocity Doppler motion along the line of sight, but you cannot, and you can measure, of course, the position of the star, X and Y, but you cannot obtain a measurement of the Z coordinate. So the number of observed quantities per star is not sufficient to derive an orbit and therefore then a mass. So this is a statistical measurement, and that's, of course, uncertain because of the limited number of stars. So how could you do this better? Well, first you want to go closer still, if possible, if they are stars. And second, you want to see accelerations of these motions so that you can actually invert the problem and find what the individual orbital motions are. That seemed very, very ambitious in the late 90s at the stage I'm talking about here, because the orbital timescales of most of the stars here are hundreds of years. So that clearly is a hard call. But then we were lucky. Nature gave us some stars which are close enough and at the same time have short enough orbital periods. Andreas' group first saw accelerations in 2000, and then one of the stars, S02 or S2, came around a peri of only 17 light hours away from the black hole in 2002. Both groups followed this motion, and that really opened the doors to precision tests, because now we could, from that one orbit alone, measure a precise mass for about 4 million solar masses. We now knew that it is within 17 light hours or fraction thereof, and that's only a few thousand Schwarzschild radii. So we really have now very, very strongly constrained the volume within which that mass is. It's the same mass as was measured before, but it's now confined to a region of about 100 Schwarzschild radii or so. And so by 2002, I think most people were convinced that this was the best evidence for the existence of massive black holes, although there were possible configuration like Fermi-Balls or boson stars or other things which you might think of that would fit in here and which could not yet be resolved by the motions. So the question is, what do you do next? Well, we knew that the orbital period was only 16 years. So we knew that the star would come back in 2018. And we felt, okay, when that happens, you better be prepared to measure so much more precisely in the spectroscopic domain, but also astrometry-wise, that we can see the deviations from Newton, see the effects of general relativity, and perhaps even get closer still to the central object. Now, I should say, of course, both groups followed these stars in the meantime through the proper motions and orbital measurements, and it's really a rather spectacular picture which we found, in that you see that the brighter stars are in a sort of a planar structure. We'll see that in a second, the O stars and Wolf-Rayet stars, while the fainter stars are randomly distributed, in fact, on highly elliptical orbits, suprathermal in distribution. Now you see the plane of the O stars. So the interpretation astrophysically is quite interesting how this all came about. Normal interactions, two-body relaxation, is not fast enough because the stars are all too young. We believe that the disk stars came in through a gas cloud, which was then shocked and became gravitationally unstable, while the innermost B stars, which are our probes, in fact, for the gravitational potential, basically are objects which came in as binaries, and then as the binary comes in, one star gets captured and the other one thrown out as a hypervelocity star, which in fact such stars have also been seen by now. Now, in preparation for the 2018 event, we wanted to make sure that we had still better resolution. And the way to do this is through interferometry. Of course, interferometry, using the interference of the light between distant telescopes, is something which the radio astronomy community has been doing for 60 years, but not so in the infrared and optical. There, the difficulty is much greater because of the shorter wavelength, because of the faster distortion timescales, vibrations, etc., etc. Nevertheless, we had that ambition to combine the light of the 4 8-meter telescopes of the ESO Para-Null Observatory, and we built an equipment we call Gravity, which does that beam combination. A very complex experiment, which Frank Eisenhower, as a PI, put together with a team from a number of institutions in Europe. And indeed, by 2016, we had installed it on the mountain, ready for the 2018 Perry. So now we had, instead of 50 milliarc-second resolution with the single telescopes and adaptive optics, we had 3 milliarc-second resolution. Instead of a few hundred milliarc-second, a few hundred microarc-second astrometry, we now had 20 to 100 microarc-second. So enormous progress. Plus, as you will see, the measurement we are doing now is basic triangulation. We don't have to rely on a reference frame, which we need to understand over a long period of time. So here is a comparison of the a very nice adaptive optics image from 2018 on the left side. So this is 50 milliarc-second resolution. Keck images would look just like that. You see the very central core of the stars, and you see that star S2. Now, if you squint a little bit, you see that the shape of the image is a little distorted. It's not a circle. And that's indeed because in addition to S2, there's also the black hole itself, Sagittarius A star, which is radiating as a variable emitter in the infrared. And so that makes the astrometry problem near Perry quite challenging for adaptive optics. Now look now on the right side. Now we look at the same little square there, 100 milliarc-second across with the interferometer. In fact, this is data taken just a few weeks ago, in fact, 1 week ago with the most recent data set. And this is really stunning in the sense that where you had one star, we now see the black hole itself, which is that yellow thing at 0, 0 in the coordinate system, plus currently 4 stars going through Perry. 4 stars. We had not expected that. The one which is labeled K equals 17 or S29 moves with 9,000 kilometers per second. So that's even faster than S2, and it's deeper in the potential than S2. But you see there are other stars. So this is a fantastic situation because now at any given time, we can really check out the potential and make detailed measurements at a level which is 20 times better in astrometry than before. So this is the picture we had with adaptive optics. And so the current situation is, as you see here, the blue curve is the star S2, which went through Perry in 2018 and is now sort of in the upper part of the orbit again, away from the black hole. But at the same time now, Perry is another star, which is that red star, which is so fast, highly elliptical orbit with an ellipticity of 0.98, coming as close as 80 astronomical units to the black hole. 80 astronomical units is about 3.5 times the orbital radius of Neptune. So this is solar system scales. And then the brown star is going to Perry in about a month from now. And the green star is going to Perry in about a year from now. So it's an incredible story. We thought after the Perry of S2, we were done for a while, but with the terrific capabilities of the interferometry, we are looking at basically New York at night. You know, it's basically so busy. And that, of course, gives us the hope to see stars which are still closer to the black hole than S2. So here's this a little blow up of this innermost region with these different stars. It's quite interesting actually to see that S2, which is the blue symbols, and S29, which are the red-orange symbols, they seem to overlap each other. And indeed, they come in 3-dimensional space within about 3 milliarc-second of each other. But the orbital, the Parry times, of course, are very different. I mean, S2 was 3 years ago, and S29 is this year. But you can ask, given their different orbital periods, when they will be in the same space, and that happens in about 5,000 years. That's a very short period of time. So clearly, the interaction between stars in this very dense innermost region is a fantastic situation. So near Parry, we can, with the interferometer, see the motion of the star from night to night. So that gives us the terrific precision on the astrometry of the orbit. Of course, we can also make spectroscopic measurements. So did the Keck group, of course, and we see in this case in the star for the star S2 how it went through the Parry and changed directions and is now going outward. Now, when you subtract the best fitting Newton orbit from the data in wavelength space, having of course constrained the orbital parameters largely from the astrometry, then you can look for the first deviations from Newtonian physics in wavelength space, and that's the gravitational redshift. And indeed, the Newton orbit is the gray horizontal line, and then the residuals of the data relative to that is the cyan black circles, and general relativity is the red line. So clearly, we clearly have seen the gravitational redshift. Also, the Keck group published a detection on this, so we are very clear. So this is the first order effect. One can see on the order of about 6 × 10⁻⁴. So you need fairly high precision on this. The next is the precession of the orbit. That should be, according to general relativity, about 11.9 arc minutes per orbit. And in fact, it's not a steady precession because the orbit of S2 is so highly elliptical, but it's more like a kink. So basically, you stay on a quasi-Kepler orbit until you come in, and then very rapidly the orbit precesses to another Kepler, if you like, 11.9 arc minutes away, and this precession near the black hole is largely in one coordinate. So down below you see the right ascension residuals from the Newton orbit, which again is the gray line. The data, again, the cyan black symbols, and general relativity is the red curve. Now you can also, of course, express this whole thing as a rotation on the sky, which is done on the right side. So you take the x and y coordinates and then look at the change of the orbital precession. Again, you see how rapidly, after the Parry in 2018, the star has now gone to a new orbit, which is about 12 arc minutes change prograde relative to the old orbit. So we've seen that, and we've seen a material much closer to the black hole. As I said, the black hole is variable, and at times it is about 100 times brighter than in the normal state. And during such times, you can actually measure the motions of the SgrA star in the infrared itself. This is shown in the upper left there as a function of time, and you can see that there is sort of a clockwise motion from the red point, which was when it started, to the blue point, more or less plausibly centered on SgrA star, which is the pink curve. So the motion here, which is at about 4 Schwarzschild radii or 8 gravitational radii, is about 0.3 c. which is what you would expect from the coordinate speed of a circular motion near the innermost stable orbit around a 4 million solar mass black hole. Now, on the same scale, the radio astronomers also can look and see a very compact radio source, which you see down below at 3 millimeters from 2019 with the Event Horizon telescope. And that fits in exactly in this sort of motion of the circumnuclear gas, which we see in the infrared. Now, this gas we're seeing here has a gamma of about 1,000, and what you're seeing is basically synchrotron emission. It's polarized synchrotron emission, and is plausibly gas in the accretion zone. We are not sure what the millimeter emission is. It could be the same. It could also be like an M87, a mixture of the photon orbit and this gas in the accretion zone, and it could be from a jet. That's not yet clear, and we do need a 1 millimeter map which could resolve that region. The reason technically why the Event Horizon group hasn't done that yet is the variability. The same variability which we can use to see the motion of the gas, they don't like, because then they cannot do Fourier inversion imaging of a long track. So that's a technical issue they're working on, and very much hope that they will have that solved in a year or two. So let me summarize, where are we after 40 years? 40 years ago, we knew there were a few million solar masses within about a few light years, or about half a parsec. So that's just on the basically the sphere of influence of the black hole. In the meantime, we in the Keck group have made ever better measurements of the stellar motions moving inward, now being obviously with the measurement of the S2 orbit having a high precision, and we can say, because we have the detections, beautiful detection of the Schwarzschild precession, that any extended mass inside of the S2 orbit can only be a few 10⁻³ of the black hole. Finally, then, the radio emission and the infrared flares tell us that the object itself is on the scale of ISCO. That's about as close as we can hope to get, so within about 3 times the Schwarzschild radius. So if you express that in terms of precision, we've come a long way. We can now measure the mass to about 0.003, so 0.3% precision. The distance to the galactic center to about 0.1% in precision. We can detect the gravitational redshift to about 4%, the Schwarzschild precession to 5%. We also can measure the equivalence principle in terms of the local positional invariance between helium and hydrogen to about 0.05%, 5%. And finally, we, as I mentioned, the coordinate speed of that gas, that hot gas near the ISCO, is consistent with the 4 million solar mass black hole. So that tells us that even in the relativistic limit, we now have, whilst not precision, high precision, but still pretty good evidence that general relativity holds, and this is indeed a mass which is very consistent with a black hole. The precession, by the way, is now so good that we can exclude any additional mass more massive than 100 or 1,000 solar masses in the vicinity. That's very interesting from a point of view of the discussions on gravitational wave inspirals and the question of the rates of extreme mass ratio inspirals, where you would think that there are intermediate mass black holes maybe going into the black hole. Certainly the galactic center seems to be a single black hole or a single central object and then relatively little else. And the stars, of course, which we see, make up only a few hundred solar masses. And then there would probably be another 10 or 5 stellar black holes in this central region. Now, I know we will come to the discussion of the paper by Becerra et al. After my talk, which is basically asking the question, could it be that the conclusion we have, that this might be a black hole, is not true after all, because instead of a black hole, we have a very compact conglomerate of a so-called Fermi-Ball. Now, of course, this configuration has been discussed before by Violier and others in the 1990s. Into first order, we felt we had excluded it, but let's look at it more closely because the analysis of Becerra, of course, is quite detailed and shows that it's perhaps possible to fit in these other this dark matter solution. Now, of course, that does not include the evidence from the innermost motion, and it does not include the radio size. It does put a lot of weight on the motion of G2, which was a gas cloud coming in 2014, and then on the way out, started to get slower. And we interpreted that to be gas in the accretion zone, which acted as a drag. And that drag can be numerically determined from the slowing down of the initial Keplerian orbit. Now, actually, the amount of gas which you infer from this, which is this red point, is fully consistent with the extrapolation of other gas measurements, baryonic measurements we have of the accretion zone, both inside as well as outside. So I think it's actually quite expected that there be such a drag on the G2 cloud. And then finally, let me just point that out again: the motions of the gas near ISCO and the size of the millimeter emission then makes the point that there has to be, if there's a Fermi-Ball, then this mass, this Oppenheimer-Volkoff mass, would have to be, say, 400 to 500 kilo electron volts, so much greater than the 50 kilo electron volts motion. But we'll, I'm sure, discuss this in the after my talk. Let me make one final remark, and that is on the magnetic field. As I said, we are seeing this innermost gas, and it's polarized. And from the polarization, we can say the following things. First of all, the polarization orbits in this innermost region near ISCO, along with the orbital time. So the polarization loops have the same orbital period as the loops in motion. And that is a very strong indication that the fields cannot be toroidal in the plane of the accretion flow. Totally unexpected, but must be polaroidal and therefore very strong. So the picture we have here, and that's actually reflected by the conclusions of the Event Horizon team in M87, is that we are not dealing with a gas-dominated inner region, but a magnetic field-dominated inner region, very much what Roger Blandford has been proposing over the last decade, such that the rotation of the black hole mediated through the fields into the circumnuclear region is of great importance. Of course, all of this has to be tested with more measurements, which we will do now that we can finally go to the telescope again. We lost 1 year, of course, because of COVID, but this year we are beginning to get good data. So finally, are we done? The same question I raised several times. And I would say we are very close. So are, of course, our friends from the gravitational waves, and so are hopefully soon the radio astronomy community with the various techniques which I described to you. But what we really have to do is to show that the no-hair theorem is correct, very near ISCO or at the photon orbit. So that this nuisance parameter epsilon is zero, and that the quadrupole moment of the black hole, for instance, can be described as a function of the mass m and the spin parameter a. So we need to measure the spin. We hope to measure the spin from stars, which are still further in. And the measurements that I've shown you give us great hope, I think, that we might see such stars as we work and also improve the interferometric techniques still more. Current measurements constrain the limit on epsilon to somewhere between 0.3 to 1. If gravity and the EHT can work together, so there is a measurement of the photon orbit and we measure the spin and the mass, then we could push that probably to 0.1. If there were a pulsar, which there hasn't been one so far near the massive black hole, then the precision of the timing on the pulsar, of course, is superior and could push that still further. I myself believe that the most likely ultimate measurement is going to be LISA, and actually following an extreme mass ratio in spiral, then you get to the level of 0.01. So that would be sort of the ultimate in the field to show that indeed, at least to ISCO or to the photon orbit, the black hole paradigm is correct, and general relativity is confirmed also in this extreme regime. Thank you very much.
Thank you very much, Rainer, for this review of 40 years of work, very impressive. And it's also very impressive that no matter what, the theory of general relativity seems to be absolutely valid and similar in accuracy to the lectures that we have heard in the first day from Kramer for the binary stars.
Yes.
The refinement which general relativity can be tested, and this is really an example, is fantastic. And I think also in our approach, we rely absolutely on the prediction of general relativity and try to see if the source can be different, but still respecting absolutely general relativity. It's about the source, the topics,
Yes, sure.
about the theory. Let's see, who is going to speak next?
I think Carlos is he not?
Hello.
There was a question. Shesheng, you have a question? Shesheng, you have a question?
No, I don't have it.
It's okay. Okay. Then let's go to the next speaker, Carlos Arguelles.
Hello everyone. Thank you, Remo. Yes, I will select share the slides. Full screen. Okay, now you see a full screen, right? Can you hear me?
Yes, yes.
Hello. Okay. Okay, well, so now I will change a bit the topic, and I mean, always related to the Milky Way, to Sagittarius A star, but in a different context, putting into the game the dark matter. So we will discuss, continuing with the, with a very beautiful presentation of Reinhard, and continue with the discussion that he put in his last slides about our last works, where we discussed the geodesics of the S2 star, but also the G2 star around Sagittarius I star, and to try to see or try to dig as much as possible if there is a possible alternative nature of Sagittarius A star rather than a black hole. So the work I will present is based on a series of several papers present in the last years, including the one of Serra Vergara and myself, Tal, in the this year, sorry. And as also rephrased by Remo recently, I would like also to stress that, emphasize that behind the theory I will present, there are also these big names in science, which are Einstein, of course, but also Fermi and Boltzmann. So 3 pillars, I will say, of physics, which will guide us or has been guiding us into conform this theory. And also very interestingly, later on, also the contribution of ideas by also Lindenberg, but in this case, in violent relaxation, which also guide us, and also Rees and Remo Ruffini also related with the possibility that massive black holes be the direct collapse of dense clusters, which in our case, instead of baryonic matter, will be related with dark matter. Okay, so let's move to the next slide. First, I will present only a few slides, very roughly, an introduction of dark matter and how this dark matter will be related to our theory. So let's suppose that we have a neutral fermion, a generic dark matter candidate, which was created just after inflation, before the CMB, before the photon decoupling, and then due to cosmological perturbations, this fluctuation in density evolved during the evolution and cooling down of the universe to form the first seeds, the first pristine agglomerations of these dark matter seeds that will then end up forming the cosmic web, and then putting the underlying gravitational potential, on top of which the baryonic matter will fill in to form the galaxies as we see today. So this hypothetical, in this case, fermionic candidate, if we think of as a cold relic, as collisionless, and in terms of collisionless fluid, it has been shown in the last decade that astrophysical observations, including CMB, BAO, Lyman alpha forest, and the local distribution evolution of galaxies, ranging from horizon scales until down to scales between galaxies, are all consistent with a universe that was seeded by a scale invariant primordial spectrum, and that is dominated by dark energy, roughly in a 70%, dark matter in a 25%, and baryons plus radiation in a 5%. So this is what gives us the lambda CDM cosmology. And very interestingly, these beautiful observations of Planck about the CMB that can be explained within cosmological perturbation theory in the concept of lambda CDM, it can be shown very interestingly that in order to explain these temperature fluctuations of this anisotropy map, the peaks of this anisotropy curve are very sensitive to the dark matter contribution, mainly, yeah, you see here in the second and third peaks that if you would like to, for example, assume that there is no dark matter at all, so the relation between the heights, the peaks of second and third, it will be completely different than observed. And also, if you exceed much more than this 25% here, you will also ruin the beautiful observations of temperature fluctuation. Therefore, out of this paradigm, there is a compelling evidence of non-baryonic matter in the CMB, and therefore it is the need to assume this dark matter reality. From the large scale point of view, there are also very precise and beautiful observations that tell us that the dark matter distributed at large scale, not homogeneously, but in a cosmic web, here in the picture of the left, showing the filaments, the nodes, and the voids. And this is the local universe, which this has been image, or this map has been superseded now with the DESS survey, which was able to photograph more than 200 billions of galaxies and making it even more precise. So if we now point into one of these nodes and want to zoom in into a halo, which is this schematic picture here on the top, observations of the stars and the movement of the stars, the circularization of the star, for example, in these galaxies, shows, as you probably know, that dark matter is needed in the, mainly, at least in the outer parts from these observations, because the circular motion cannot be explained. The circular motion, which follows this trend in circular velocity, cannot be explained with the dark matter, with the baryonic only contribution, which is expected to follow a Keplerian law instead. So, and the topic of my talk will start here with the halo of galaxies, and I will also to stress that the particles I will talk about are neutral fermions. Very interestingly, you can track them as in the very early universe when they were born, to then how they evolved from cosmological perturbation theory to form the large-scale structure, to then conform a halo when relaxing, and then, as I will show, they can also play a role in the central region of galaxies, including around. So now let's move to the model itself, how fermions, when self-gravitating, when they relax, form dark matter halos in galaxies. So the first key concept here is to say that the fermions, neutral fermions, can, under self-gravity, do admit a perfect fluid approximation. This was demonstrated in this original work of Vina Morasola in the 69. And then one is able, it's possible then, after this, to use the Tolman-Opec hyperbolic equation for a semi-degenerate gas of fermions in hydrostatic equilibrium in spherical symmetry. And so this kind of, as Gensel showed recently, this kind of, in the last talk, this kind of equation were solved in this context of fermions in the early 90s. Well, the first work was in 1990 in the Gao Ruffini et al. To show in general relativity that you can obtain this dense core diluted halo profile for dark matter, but then they were applied later on for Violier, Muñoz et al. To try to explain this central contribution of dark matter at the center of galaxies. But in their case, it is important to stress that they were working under fully degeneracy approximation. And in this case, I will show that when you include finite temperatures of fermions, which is very important, but also scale velocity of particles, including for evaporation, you live with a most general solution, which is the one that can gives the much richer phenomenology, as I will show in a moment. So let's, these equations are the first two equations. You probably recognize these are written in dimensionless manner, but the first two are the Einstein equation, the only two relevant for the spherical symmetry equation of a state, which is the mass equation, the TOV equation, the second, and then the Klein and Tolman isothermality conditions, and then the energy conservation along geodesic, written in this manner. So this equation of equilibrium has to be given the source of matter, which in this case, of course, will be the equation of a state will be written in terms of this fermionic phase, coarse-grained phase space distribution, which I don't have time to show the details here, but I refer to the plenary session I gave on Thursday to show that this kind of coarse-grained phase space can arise from a violent relaxation mechanism, including for the quantum nature of the particle, and then it can be obtained just in a realistic relaxation mechanism to then plug in this equation of state, who in turn will play the role of the source of the Einstein equation. So this is the relativistic energy of the particles, which include all regimes, either non-relativistic or relativistic, depending on the momentum. And then, of course, this is a boundary condition problem of this, because this is a coupled nonlinear ordinary differential equation where you have to put boundary conditions at the center. We will put regular conditions, so the mass at the center is not singular, it's not a singularity, it's regular. Then we will search for general solution with high central degeneracy, theta 0, which is mu over kappa t, then the temperature parameter beta, and then the cutoff energy parameter. So here are the 4 free parameters of our theory: particle mass, the temperature, degeneracy, and cutoff energy, and has to be given at the center to try to find the most general solution. So this is the solution that Rainer shown in his talk about the possibility to have this dense core concentration of fermions at the center of a spherical distribution of in the halo. And so the most general solution, as I'm showing in this plot, shows a central concentration of fermions which is holds gravity due to degeneracy pressure. So here is Pauli principle acting, but semi-degenerate, not fully degenerate. So temperature is not tending to 0, but finite. And this transition in a continuous manner when to the Boltzmann-Bosmanian distribution function, where now the pressure is held by thermal pressure. So it includes both regimes, and it's important that the boundary conditions of this kind of solution here are typical of spiral galaxy halos. These were chosen purposely this way. So you can see that in this transition from core to tail in the density, it goes to 10 to the 4 parsec, typical of halo scale length of spirals, with masses about 10 to 11 for this case. Important point is to, as I said, that the central concentration, we can demonstrate that fulfills the quantum condition, meaning that the thermal de Broglie wavelength inside the core fulfills to be larger than 3 times the interparticle mean distance. And another important point is that these profiles depend on the particle mass, which is another very interesting aspect of this kind of models, because you can constrain the compacity of the central cores when you change the particle mass, which, by the way, these particle masses can also, the numbers can also be in agreement with that, demonstrate with a large scale structure of the universe and with a primordial candidate of their matter. So now let's move to the Milky Way and to, well, the details proper of this discussion. And first, let me very briefly run along the main observations of the Milky Way. So we have, we know, at least at first order in the Milky Way, we have a very central parsec, governed by a dark compact object, presumably a black hole of 4 million solar masses, as Rainer showed recently, very splendidly constrained by all the observations of either gravity collaboration on the American team in the last 8 years. Well, then the central kiloparsec outerwards, which is governed by an inner and main spheroidal bulge. Then we have the disk at 10 kiloparsec roughly, and an outer halo spherically governed by a dark matter with this number. So first, probably the picture you recognize better is this one at the bottom right, which is the data of circular velocity in the halo in linear scale. And I interestingly also to show the circular velocity in log scale, when we can cover from the first parsec, so you can join, let's say, the circular velocity at least effectively in this is the peak of the bulge inside effectively, because the error bars here, of course, denote for non-circular motions, because towards the center of the galaxy, we have a bar and a non-circular motion band. Effectively, in an effective rotation curve, this you have here around 30% of deviancy for circular velocity, which can be constrained here, and will also be used to constrain our model. Because as you saw before, our model runs from the very center of the galaxy until the outer halo. But now, in order to ask for all possible constraints towards the very center, of course, this was explained in detail in the last talk. Let me just recall that this is we have the S-star clusters, which were observed by near infrared techniques, with the S2, the one that up to now is better constraining the central object, but there are other somewhat closer stars towards the center, respect to the center, and the nice G2 or gas stripping objects like G2, which we also include in our analysis, which is these objects is nowadays believed to be of stellar nature, not of gas cloud, because otherwise high-resolution simulations are showing that they should have been stripped off after pericenter passage. So I recall the observations. Well, these were a bit of some years ago. This constraint of 4.2 million solar masses, it has to be necessarily inside the first milliparsec. And this, as I said, this has been beautifully updated in the recent years, also accounting for relativistic redshift of S2, also by complementing all these results also by American team. So the key question here of this talk is, of this discussion is, can these novel profiles of fermions, of a dense core diluted halo, their potential can explain the Milky Way rotation curve together with the S-star dynamics, but also G2 without assuming a central black hole? Well, you have to solve the boundary condition problems that I shown before for specific values of mass at the core, but also to follow the constraints of the mass at the halo scales, including, we have also included the constraint of Sagittarius dwarf satellite to constrain the mass outside. And so this I show that for the first time, a solution of this dense core dilute halo nature of fermions, that the first time it was possible to have a solution that can, the fermion ball inside can be inside the S2 pericenter, while the outer halo can also explain the rotation curve, was in 2018. In this work was after I finished a postdoc here in Italy, and for the first time we extended the more simpler solution of Violier of early 90s, and also of others who deal with this kind of profile, but that formerly they were only doing without taking account the evaporation of particles, and therefore the outer halo was following a 1/r² that we know these profiles are not that much realistic, because you have to bound in some box. Well, in this case, you have you have the similar dense core of fermions, dilute halo that I showed before, but in this case, the size and total mass of the halo is naturally finite. And the most interesting is that there is a family of solutions, as I show here, between the black curve and the gray curve from particle masses between 48 keV and 300 and nearly 350 keV, which is, this is the, as I think said Reynard about the criticality of these cores. Well, when you have a finite temperature, the criticality of this core is 345 to have a 4.1 million solar masses critical object collapse into a black hole. Here is the critical mass. And all of these solutions between the one of 48 keV up to the one of 345, the dense fermion core is dense enough to fill inside the S2 space, the S2 star pericenter, which is this star, blue star here, put here as an average circular velocity of this star in this plot, because this is rotation curve or circular velocity of object. It is very interesting that in this kind of models that the solution transition naturally to this halo region. So here is quantum fermion degeneracy, transition continuously to Boltzmann. But in this transition, the minimum is not spoiling, incredibly the baryonic contribution that has to be there, meaning this green curve is the bulge, while the dashed green is the disk, which we used as obtained from observations to constrain the rotation curve data, but then rises in the outer part when it is needed, roughly at about 8 solar neighborhood, rises with a contribution needed to explain this flat, nearly flat part of the rotation curve. Okay, but this, well, this is assumed in the outer part to show that both an NFW profile, traditional seed colder matter paradigm, and ours can both fit very well the rotation curve in the outer tens of kiloparsec. But of course, if one wants to put better constraint to Sagittarius A star, one needs to analyze geodesics and compare with the prediction of, for example, Schwarzschild black hole. So we have done this for the first time in 2020 in this paper published in Astrophysics, where we have used all the data available at that time from BLT, or at least publicly available from BLT, Keck-12, Gemini North, and Subaru. And so we had the challenge that to explain the multi-year accurate astrometric data of S2 star around Sagittarius A, including, of course, for the relativistic redshift, but also the available data of the G2 orbit, and including for the G2 post-pericenter passage, this deceleration, which, as Reiner recall us, can be explained in the black hole paradigm, though invoking a drag force in an accretion with some specific physics of accretion. Okay, so the S2. So these gray dots are all the data we recollected in 2020, and we compare the models by solving or calculating the geodesic equations of a test particle in the gravitational field, first of a Schwarzschild black hole of 407 10⁶ solar masses, which is produced the best fit to this position in the sky of the particles, right ascension and declination, of 3.3 roughly average chi-square, while there is a best fit in a good fit in the dark matter fermion core in this case, and a core mass of the fermion of 3.5 10⁶, reaching a statistically slightly preferred chi-square for this fitting. So though very similar, but slightly preferred. So both models up to S2, at least as the data collected until the last year, can be fit very well with the same statistical, nearly same statistical accuracy. And then we move to the line of sight radial velocity, or sometimes called the Z redshift of S2 around Sagittarius A. And we can see as well that both models can fit very well this data with similar chi-squares, as I will show later in the table. But I want to stress that the important point that both models can, well, of course, the black hole has been shown very nicely to, for the first time, show the relativistic excess of this line of sight radial velocity, and in the dash is Newtonian, so we cannot be clearly explained only by Newtonian gravity, but general relativity can account for this excess of redshift. but our model can explain with the very similar accuracy this data. So our model can also account for the redshift of the STU. But now let's move to G2, which is very interesting case for our model, because where we have proceeded similarly, calculated geodesic equation of a test particle, again in the gravitational field of a Schwarzschild black hole of 407.26 solar masses, and in the fermion core with a 56 scale, and both models can reproduce very well the position, slightly different. You can see here, then I will show in the table the numbers. These are similar statistical numbers, but the first key result here in our model, what was really surprised us when we saw this result, is that for the same particle mass that one reproduced as 2 star and velocity, fit the post-pericenter passage, as you see here, this 3 point of G2, that in blue is the black hole only, with much better accuracy. You can see here the reduced chi-squares. In the case of black hole is 26, and in the case of RAR is nearly 1. And therefore, here is the residuals to show the clear difference. And this was very intriguing because the same dark matter concentration can explain the post-pericenter passage without to invoke this drag force, which either if it works, it needs to assume some, let's say, not well understood assumptions. For example, in order to explain this, they had to, in that paper, they had to assume that the G2 is a gas cloud. But as I said before, the gas cloud hypothesis is not totally accepted or even quite tensioned, because it should have been stripped off by the pooling of the central object, as shown in another works, and also the density, the environment density needed for these objects, either if you assume that it's a gas cloud, has to be extrapolated, and it's not clear which is the physics there. But just to, this is, I think, is the first key result of our model. And then we extended the phenomenology and include the 17 best result as stars, as you can see here, up to late 2020. We published this year. And again, we calculated the geodesic equation either in a Schwarzschild black hole metric of this mass, and in the case of dark matter fermion core, again of 56, again in the case of 56 kiloelectron volt, and showing that the average of the reduced chi-square, including position in the sky and radial velocity, line of sight, so the average of all the 17 along all the data is slightly prefer again our model of dark matter respect to the black hole, or respect to at least the Schwarzschild black hole. Well, this result was published this year in this monthly notice, when we said that this 56 keV dark Venus not only can explain the galactic rotation curve data and the G2 without any drag force, but also the 17 best result as stars. And here, please let me say that I will not show in this talk, but let me say that this is even more interesting if one considers that for the same particle mass, one can explain with this kind of core halo profiles for different temperature parameters and degeneracies, the rotation curves of dwarf galaxies, other spirals, elliptical galaxies, and even clusters. So, and this is, we believe, is very intriguing, the solution, which are Einstein solutions in spherical symmetry, to not only, the particle mass can not only explain for a large scale structure of the universe, but also relaxing halos, and explain for a plethora, huge plethora of galactic halos, including the Milky Way and including this precision towards the center of the orbital motion. So this is, we believe, we have to, are obliged to keep forward in this endeavor, because it seems to be quite it cannot be that coincident that all these regimes are in order with these particle masses. And so, well, here I will end now, and this is the table of all these stars with the reduced chi-squares, but probably other colleague of our team can explain better the differences. And so let me conclude that accounting for a quantum nature of the dark matter particles in the relaxation of halos, accounting for a dark matter particle in the relaxation of halos, which indeed are not included in usual cosmological simulation with classical particles, can lead to novel core halo profiles with a dense core of fermions surrounded by diluted halo that for 50 keV particle mass, about both either a black hole paradigm or a dense core, this kind of dense core of fermionic dark matter can both explain the precise astrometric data of S-star clusters, including S2. And but in the dark matter paradigm, besides the S-cluster and the Milky Way rotation curve, they can also be in a unified way explain the post-perecenter passage of G2 without the drop force. Of course, there are open questions, which I think are very interesting to pursue and to discuss, which are how these fermionic cores affect the gas accretion in these such low luminosity environments as the surrounding of Sagittarius A. Can it help, these models can help to resolve the paradox of youth, which is a problem which I think Reynard mentioned very briefly, but which tells us that it is not expected that these cluster stars, which are quite young, are there because the conditions, the gas, when the pristine gas clouds will have to collapse to form these young stars. If they are in the context of environment, a black hole, it should have been possible to be formed. So maybe if you don't have a singularity, it may help. So this is an open question. And finally, given that the extended dark matter mass, the surrounding this core, if they can improve or not the orbit precession of S2 around Sagittarius A. Okay, I will stop here, and thanks a lot for your attention.
Thank you very much, Carlos, for this interesting presentation. Can we hear maybe someone have a comment also from Rueda or Krut or Becerra?
Edward, you would like, I don't know, you would like to mention about the fittings?
Yes, I want words noting that in the table you sent.
Let me put the table.
Yeah, the last table is important note is if we consider a difference in the first decimal of the reduced chi-squared average, then the RAD model fits a little better 5-star S2, S18, S19, S21, and S31. While the black hole model only fits S2 better than the RAD model, and the other 11 stars are equivalently fixed for both models. This is an important part for the variable of the statistical relevance, the reduced square sign order. In this study of 17 stars, the RAD model explain a little better or more star than the black hole model.
Okay, thank you.
Can I just make a comment?
Yes, Jorge.
Yes, first of all, to thank you both. Thanks, Professor Gensel and Carlos for these very interesting talks. Professor Gensel talk was very beautiful to see all the story, all the history and the story at the same time of all these technological developments which helping us to understand what is the nature of Sagittarius star. And there was also in the talk of Carlos, I also see that there is also in parallel another journey, which is a theoretical journey in which are a lot of concepts that have been coming out bit by bit through decades, which have helped us to formulate all this theory. And about the data, I will just to mention that actually we are not pushing at the moment. We don't need to push very much pressure on pressure in the sense of attention to the case of G2, because actually the data, which is of higher quality of all the rest of the S stars, are well fitted by our model. So it's not a question of G2 or not G2. This is just a comment that I would like to mention. And about the new objects, these S55 and these other stars, we are looking very much forward to the fit of this new data, which I think, as Carlos showed, the compactness of the core is a function of the mass of the particle. So it will be very nice to see if this new data will just give us a different value of the mass of the fermion, which it would be maybe a little bit higher than 56 keV, maybe 58 keV, maybe 60 keV. And the same for the new data, for the forthcoming data of the precision of S2, that we are looking very much forward to that, to see that always that would be also a key information for the determination of the mass of the particle, the mass of the fermion.
It's very exciting, and I hope Reinhard will transmit to us the data as soon as available to allow us to make this refinement. I think also it already from the result we have, I think the solution must be very, very close to a Schwarzschild-like solution. And I will consider, well, we can certainly do a perturbation analysis to show the effect of the spin, a net spin of a Kerr solution in this system. But I think the constraints are very strong, but this is my personal opinion for the spinning object. Okay, I think the time has come. Reinhard, you have a comment?
Yeah, you allow me to make a few comments.
Yes.
I mean, obviously, we all agree that this exercise is, very important and valuable. I think I would fully agree with that. We all agree, I think, qualitatively, that whether or not a soft potential, let me call it a dark matter distribution, a soft potential, okay, as compared to a black hole solution, soft on the scales of, 1,000 or at least a few hundred gravitational radii, whether that's allowable or not. Obviously, that is without any doubt, can only be tested either through very close objects and alternatively through high precision measurements, okay? Because any deviation from, a 1 over r squared, if you like, classical potential, would be seen in things like the Schwarzschild precision, et cetera, et cetera. Now, I do point out that you've chosen not to take into account SgrA star and the ISCO motions. Okay, I think whether or not that's fair, I leave that to you. I find it, you at least you would have to think how you then explain the presence of emitting baryons in the center of your fermion dark matter core, right? I mean, that's the least you would have to do. They're there, okay?
Yeah.
They're there. We see motions, etc., etc. In your paper, as I understand it, let me first say something about G2. I think please, I would ask you to remove G2 from the discussion, because the data on it are far less good than the stars. Okay, that's just the object is a we observe the object largely in line emission. And so the astrometry is not as good as we have it even in the adaptive optics data. So, and by the way, we have now stars which cover the same outer, if you like, outer region in radius as G2. So if G2 shows it's important for your model because of the slowing down, then there's something wrong, because the stars, which are in the same volume, don't show any slowing down, so to speak. If you fit for any of the other stars a mass model, you get the same mass as with S2. So that tells you right away that, okay, G2 is let's leave out the discussion whether or not there's gas. I think for me it's clear. It's very, very clear that it was disrupted and it came back together. And the fact that it is actually compact again is exactly what you would expect if the density of the accretion flow is low. But anyhow, I would suggest leave out G2 out of the analysis, instead take other stars. Now, as I see it, the analysis you've done, you've based on the published information. So that's the adaptive optics data sets, presumably, and in particular, Doe et al. Now, you do realize that what I showed today are data which astrometry-wise are 30 times better than what Doe et al. Have. And that's a very, especially near Perry, because near Perry, if you take an 8-meter telescope, your diffraction resolution is only 50 milliarcseconds, while the star passes as close as 20 milliarcseconds to SgrA star. SgrA star is emitting almost all of the time. So your centroid during Perry of the adaptive optics data sets are being pulled. We can see this in our own data. And in fact, you have to throw them away, okay?
Yeah.
So the critical thing is to use the astrometry of the interferometry, which is that much better. And the fact that I told you today that we have a detection of the Schwarzschild precession to 20 sigma should tell you something, because that is in essence a direct statement about the nearness of the potential to a point source.
Can I comment?
Sure.
Yes. So this data of more precise than Doe et al. is publicly available now.
Well, okay, we have not done that, and it's a question how soon we will do that. The reason is interferometry is a very new technique, okay? And in 2018, well, okay, the 2020 paper on the Schwarzschild precession, for instance, we were still obviously then working on various details on systematic effects, and we still are. So what I don't want, and we've decided that here, what I don't want is that we put out, publicly available data, and then you all interpret them without knowing how much systematics there is, and then you make a theory about it, and then 2 years later, we have to tell you, I'm sorry, yeah. So
no, for sure.
I mean,
we can wait for that.
In fact, if you look through the Doe et al. Paper, Tuan Do also points out the danger of the systematics at that level. So I'm a little, I would say, hesitant to throw these data on the market, so to speak. More important, the question is, well, one could talk about collaborations and so forth, perhaps, to do this inside, so that one has a control of the systematics effect. But in any case, think about what that means, that a potential is such that a Schwarzschild precision is measured to 20 sigma.
Yeah,
may I make a comment?
Yeah, then I want also to make another comment.
First, okay, I feel a bit puzzled with the comment on the data, because first you ask us to use your better data, but data is not public, so we cannot use that. So we cannot go over this cycle. So we can use what it is public. We were the first to ask to people of gravity collaboration about that, and the answer was not. You cannot use. There are no public data on that, so we cannot do that. And when the data will be public, it will be a pleasure to do that, to use the data to confirm our predictions. But even if you compare the analysis with the data that is public and with data of the gravity collaboration within a black hole hypothesis, I mean, the results of the gravity collaboration, the results of the Do et al. Are not very far away. So I think that even what that data will public, I think that if the mass of it will come instead of 56, maybe it comes 55 or so. It will be not a big difference. This is my guess. But anyway, and I think there is a confusion. Our model is not Newtonian. Our model is general relativistic, fully general relativistic. It's not even post-Newtonian. So it's full general relativistic geodesics. So when Carlos showed that actually we also can see the deviation in the gravitational redshift, it is not effect of dark matter of a matter as such. Because the gravitational field is general relativistic. So this is a clarification that I would like to say, and is the same for the precision, which is on which we are working, and we are going to present something very soon.
Yeah. So I would like to make one short comment about precision and this claim of 20 sigma. I don't know, Rainer, at least I have heard very recently a claim for the American team that precision may not be prograde. Mm-hmm. Have you heard about?
Let's stick to the data, and let's lead to the official statement and publication.
Okay. Thank you very much.
The rumor, especially in this very delicate situation, I will leave the rumor out. We are ready to examine with them the data and with our theory. We are ready on that, it's no problem. But please, let's not speak about rumor. We have some results. As soon as we will have the results about the precession, we will publish, but not rumor, please. And well, anyway, I think we have to close, because I see some of our distinguished members of the International Organizing Committee which are waiting for the conclusion. And thank you again, Reinhard. Thank you everyone for this interesting, and as the poet of Pescara said in Latin, ad maiora, namely, let's go to greater results. And I think we are going in this direction. Okay, thank you so much to all.
Thank you.
And now I would like to ask, first of all, I see Rashid Sunyayev, I see Razmik Mirzoyan, I see Tzvi. Today, Sabat, you make a special effort to be with us, and thank you. And I would like to ask, well, first of all, if you have some comment, but then before that, I would like to go to some official statement from Gregory about the proceedings and all that, and express already now the incredible, enormous work that they did, coordinated by Gregory and the secretaries and the technician. I am really surprised after seeing other meetings where so many problems are the perfect development of all this MG16, and how exciting has been to use this technology of communication. I think it's really essential from now on to use that for scientific exchange, etc. Where are you, Gregory? Can you say a few words?
Yes, thank you. Thank you. I will just want to share a few facts about this meeting. Maybe if you allow me to show you a simple diagram. Okay, this is a number of participants. So you know very well we have more than 1,100 participants actually at the meeting. So this is distribution with countries. You can see United States as usual dominate, but we have many participants from Europe, Italy, Germany, UK, France, and so on. And we have, of course, other continents, China, Japan, Australia, Russia, and also Brazil, South America. So this is, of course, truly international meeting, as you can see. A large number of talks were present at this meeting, more than 1,000 actually people spoke. More than 80 parallel sessions were organized by more than 100 chairpersons of these sessions, 9 plenary sessions, 5 roundtables, and including the last one, the last 2 very interesting yesterday night and today. And we also would like, of course, to say that the proceedings traditionally published by World Scientific will be published also for this meeting. We'll change a little bit the plan because even last proceedings were electronic, and including this one will be electronic as well. So we'll try to collect as fast as possible the papers from the participants. And we will start, we hopefully start accepting papers already from end of next week. And we'd like to fix the deadline as soon as possible, September 30. But anyway, we will publish all this on the website of the meeting and try to send everything in print by the end of the year. And of course, it gives me a particular pleasure to thank all the members of the local organizing committee who actually worked very hard on organizing this meeting. I'd like to say their names: Cristina Adamo and Silvia Latore, our administration staff at ICRANet, Cinze and Nicolò and Elisabetta Natale, the secretaries for handling all the communications with so many participants, especially overseeing this very complex program of the meeting. Carlo Luciano Bianco for his great help in handling test meetings for Zoom. This is fully new to us, but we did it actually, I think, very good. Besides being also chairperson of the parallel session. Gabriele Brandolini and Domenica De Silva da Silva is our heroes, actually, who supported all the technical side of the meeting, and in particular, very hard work on the 30 parallel sessions we had simultaneously every day. Our special thanks goes to the team in China, Yuan, Yifukai, and Daniela Gregoris. They all three were actually, they made possible all the sessions, first block sessions, which started otherwise too early in the morning for Europe. And I think that the meeting went well, essentially thanks to the spirit of collaboration and mutual support developed in our team. So we hope to go further with this spirit. Thank you all so much for participating, and I hope we meet finally in person, hopefully in 3 years after 2024. Okay, Professor.
Well, let me add all the thanks that Gregory did, of course, from my own side. Before I go to sum up, let me ask Rashid if he has any comment.
I don't know, this was very interesting conference, not only previous to lectures, but a lot of plenary. I attended a lot of plenary talks, and many thanks also for copies of the YouTube stream, because it's possible to return to check numbers in the most interesting talks. I'm very grateful for this. And I was participating in the work of three, but just not as a speaker, but I was participating in the work of three parallel sessions, and they went and were organized extremely well. I also believe the team, that the local organizing committee and Gregory Vereshchagin made really great job, and it's very, very good. And I wish Rem that there will be no pandemic in the 2024, and next Marcel Grossman conference will be as interesting as this one. And I think that online version is going really very, very well. Thank you for organizing this meeting.
Thank you, Rashid. Razmik, you have any comment? I see you there.
Yeah, I will just join what Rashid Aliyevich told us. I enjoyed the conference very much. I think I learned a lot. I appreciated very distinguished speakers talking about very, very interesting scientific topics. I think it was very well organized, and the Zoom was working in a fantastic way, in my impression. Of course, I immediately agree that Grigory Vereshchagin did a fantastic job. I experienced it just because of my parallel session, but many things needed to be adjusted. So I think this is a great conference. I would like to thank Remo for organizing this, and then the entire organizing committee, and all the distinguished speakers. So, but I think maybe unlike you, I'm a little bit more optimistic about pandemic. So I do not think that it will take another 3 years. I hope very much that next year, starting next year, we can have face-to-face meetings already in quite safe conditions. And then I think we will resume our face-to-face meetings, which has another quality, higher quality. Thank you very much.
Thank you, Razmik. And Zvi, you have any? Are you there?
Yes, I'm here. I would like, I somehow do not manage to switch on my video. I'll try it in a second.
Where are you?
I just arrived back home. It was a complicated story. Back home in my study. Okay, yeah. So I would like to thank again, the previous speakers, the organizing committee. This was a fantastic job, and I was in particular admired the carefulness in which the timetable was arranged so that people from all over the world could join. I noticed the shifting of the sessions from one continent to another continent was amazing. And it shows, among other things, something that Remo has pushed for many years to show how global is this community and how international is the search for new understanding of this theory of relativity. And I was also extremely impressed by the scope of this meeting that ranged from details at the level of modeling of new ideas about the entropy of the black hole on one hand to relativistic astrophysics and presentation of dramatic almost results from various experiments ranging from various observations. So this was a fantastic meeting, and I want to thank again everybody involved, in particular Remo, but also Gregory, for this amazing organizational effort. And I share the hopes that looking forward to see all the participants in the next meeting on live in the next Marcel Grossman.
Thank you. Thank you, Zvi. Well, I will not be long, but I personally enjoyed very much every moment, even this morning at 6 o'clock. And the important point is that we have all on tape on YouTube. And we are going to try to keep the entire conference available to everyone, or to organize all the presentation to be available electronically. Because I think this is a unique, the first time that this can happen. But at the same time, we have been extremely lucky. There is changing relativistic astrophysics. The emphasis is changing. We have, of course, the great new instruments which are coming in vehemently. We have seen the radio observatory in China. We have seen the beautiful presentation of the new mission from China, from Nanzang and his collaborator. We have seen, of course, the #1 winning the award, the great mission organized by Rashid and the Russian and Max Planck extraterrestrial physics of the great mission, which is now in the Lagrange point outside the moon. But all this make us think that the development are going to grow enormously. But there are things which have been evolving in real time. I think the TeV radiation is one of the great new message that we are opening a new domain, not just very essential. And the good development we have seen from the ground observation of TeV is really, and the latest result in the few recent hours from China, the TeV radiation, is not only the data are interesting, there is new physics, there is completely new physics coming on. And the GRB, of course, have been the major vehicle which has allowed to understand new physics and even to identify in this 50th anniversary of my work with Johnny of introducing the black hole. After 50 years, we finally found the way to convince even Roy Kerr that this solution is not just beautiful and unique in mathematics, but is essential to explain the energy extraction, that energy which we introduced when we were much younger with Dimitrios Christodoulou, the extractable energy. There are still mystery, even in that formula, even in that irreducible mass. But this opened just a new frontier in which we are much, much stronger from observational point of view and conceptually ready to new analysis on new time scale and to the quantum. This is the greatest message which I think has been new and carried out in this meeting. The fact that we are ready to see not only the classical general relativity, but in a classical background, quantized effect at astrophysical level. this is the message I sent today, and I just have to have a caution. I have always been in some difficult time to use the classical word of Eugene Wigner. Interesting was the word that the message that Wheeler told me found the secretary of Niels Bohr. There was a message, interesting, equal, wrong. Well, Eugene amplified this message very politely, always, very interesting, if true, equal, totally wrong. I have kept many times this attitude of using both words, interesting and very interesting, in some cases very interesting if true. But I would like to make sure that people consider also the necessity of being accurate in creating good data. Because if the data are not good, we have to apply the famous word of Pauli. This paper is not even wrong, because if the data are not good, it's not even possible to establish if a paper is right or wrong. Therefore, please make an effort to implement good data analysis, and let's move forward. And I think relativistic astrophysics will keep growing as one of the most successful areas of human knowledge. And we are understanding a lot, thanks to all our friends. And to all, not only friends, but thanks also to all scientists on the world. Thank you. Sono ancora.